Hello and welcome. Today I would like to talk to you about something called contrastive learning. This is a difficult topic, but I hope that I have made it a little more accessible. I'm going to show you an article first, and then I'm going to do a demonstration. So anyway, let's get started. And here we go.
The Secret Behind How Computers Connect Images and Words, Michael B. 6 Minutes read, 3 hours ago, by Mike B., AI Research Communicator. Have you ever wondered how a computer can not only tell a dog from a cat in a picture, but also connect that image to the words fluffy companion or playful pet? The answer lies in a powerful technique called contrastive learning. In this article, we'll explore what contrastive learning is, how it creates connections between images and text, and why it's revolutionizing how computers understand our world. What is contrastive learning? Contrastive learning is a way to teach computers to understand things without having to label every single example. It's like teaching someone what a dog is by showing them lots of dogs and saying this is a dog, and showing them cats, horses, and other animals and saying this is not a dog. The computer learns by comparing things, pulling similar things closer together and putting different things farther apart in a special kind of space. How does it work? Understanding dimensions. Every image or piece of text has many dimensions, which are simply different characteristics or features that describe it. Think of dimensions like a super detailed checklist of qualities. For an image, these dimensions might include the color blue. How blue is it? The color yellow. How yellow is it? Having a cat in it. Is there a cat? How prominent is it? Containing flowers. Are there flowers? How many? Being outdoors. Is this outside? How certain are we? Having water. Is there water visible? For text, the same dimensions exist. Words and phrases also have values for dimensions like blue, yellow, cat, and flower. Now imagine a space with hundreds or even thousands of dimensions, not just 2 or 3 like we can visualize. Each dimension is like a different axis on a graph. An image or text gets placed at the exact intersection of its values across all these dimensions. For example, a photo of a blue cat playing with yellow flowers outdoors might have coordinates like blue dimension 0.8, high value, very blue, cat dimension 0.9, high value, definitely a cat, yellow dimension 0.6, medium high value, some yellow, flower dimension 0.7, medium high value, flowers are present, outdoor dimension 1.0, maximum value, definitely outdoors, water dimension 0.0, zero value, no water at all. A text description saying a blue cat playing with yellow flowers in the garden would end up at almost the exact same point in this multi-dimensional space, because it scores similarly on all those important dimensions. How contrastive learning shapes this space. Before contrastive learning, computers had 2 completely separate coordinate systems, one for placing images, another for placing text. These 2 systems didn't align at all. The cat dimension in image space had nothing to do with the cat dimension in text space. Contrastive learning transforms both of these spaces so that they align perfectly. It reshapes both spaces by 1. Pulling matching pairs closer together, like an image of a dog and the text dog. 2. Pushing non-matching pairs apart, like an image of a dog and the text airplane. Through millions of examples, the computer gradually reshapes both spaces until they align perfectly so that the exact same dimensions are used for both images and text. Why it's special? What makes contrastive learning truly revolutionary is that it's a form of self-supervised learning. This means the computer learns from the data itself without needing humans to painstakingly label every single example. The matching of dimensions is also super efficient. Instead of the computer having to learn what blue means twice, once for images and once for text, it learns it just once in a shared space. This shared dimensional space is helpful because 1. The computer can generate connections between pictures and words by comparing their positions in this space. 2. If you search for blue cat with yellow flowers, it finds images that are located near that text in the dimensional space. 3. It can even understand new combinations it hasn't seen before, like if you ask for a purple cat with red flowers. Real-world impact. This technology powers many things you use every day. When you search for cute puppies and the computer finds matching images, when your phone automatically organizes your photos by what's in them, when a website suggests products similar to ones you like, it's important to understand that the computer isn't retrieving pre-labeled images when you search. Instead, it's using its understanding of the shared dimensional space to generate responses that match what you're looking for. The computer is actively figuring out which images are located near the text cute puppies in that multidimensional space. How it's different from traditional methods before contrastive learning. Teaching computers about images and text was much harder. Traditional methods contrastive learning, requires labeled data, lots of it, learns from unlabeled data, learns separate models for images stroke text, creates a shared representation space. Less efficient, more data needed, more efficient, less data needed, struggles with novel combinations, handles new combinations more easily, going deeper. For high school students, transforming latent spaces while preserving structure. When computers process images or text, they convert them into what we call latent spaces. This is just a technical term for the multi-dimensional coordinate system we've been discussing. Each image or text description gets mapped to a specific point in this space, a point defined by hundreds or thousands of dimension values. An image of a blue cat and the text blue cat should end up at nearly the same point. A crucial point to understand is that these transformations preserve the internal structure of each space. It's similar to how a cube remains a cube even when you rotate it. The image model remains an image model, and the text model remains a text model. We're just reorienting them to align with each other. Think of it like two different maps of the same city, one showing streets and one showing subway lines. If you rotate and scale them correctly, you can overlay them perfectly without distorting either map. The relationships within each map stay the same, but now they align with each other. This preservation of structure is why the models still work effectively. We haven't distorted the models, we've simply reconfigured how they are oriented so that similar concepts align across both spaces. But this alignment doesn't happen automatically. The computer has to learn how to place things in this space, which brings us to the loss function. The loss function, teaching computers what matters to align these spaces. We need to tell the computer when it's doing a good job. This is where the loss function comes in. In simplified form, the loss function looks something like loss equals distance, matching pairs, min, 0, margin, distance, non-matching pairs. What this means in plain English, for matching pairs, like a cat image and the word cat, make the distance between them as small as possible. For non-matching pairs, like a cat image and the word airplane, make sure the distance is at least some minimal amount, the margin. With every example, the computer says, it adjusts how it places things in the dimensional space to get a better score on this loss function. Over time, this reshapes both spaces until they align perfectly with the same dimensions, working the same way for both images and text. Efficiency through shared parameters. The real power comes from what computer scientists call shared parameters. Instead of having separate rules for understanding dog in images and dog in text, the computer learns a single set of rules that works for both. This shared understanding is much more efficient, requiring fewer parameters, rules, in the computer's brain and leading to better performance with less training data. When generating responses to your searches or questions, the computer doesn't retrieve pre-labeled answers. Instead, it uses its understanding of these aligned dimensional spaces to make new connections between concepts. The big picture contrastive learning helps computers understand our world more like we do. When you see a picture of a beach, you automatically think of words like ocean, sand, and sunshine. Now computers can make these same connections by finding items that exist at nearby points in their multidimensional space. The next time you search for something online and find what you're looking for, remember that contrastive learning might be the magic happening behind the scenes, connecting words and pictures through shared dimensions in ways that make sense to both humans and machines. Want to see contrastive learning in action? Try searching for unusual image combinations online and notice how well modern search engines can understand what you're asking for, even if those exact combinations don't exist in their training data.
All right, so let's take a look at this. We can see the text space is moving to the text space area. Now, this animation is showing this happening separately, but actually, these two spaces will end up one on top of another, not side by side. This animation, however, does treat them as separate spaces. You can see they're starting to look very similar in their alignments. And there you go. The one will go right on top of the other. Now, if we were to train these models separately, have two separate models, they would look very different. They would probably be a different scale. They would probably be rotated, etc. But the underlying semantic structure has a shape. And this is important. We should realize this. Semantic space has a perfect shape, and we try to approximate it. Anyway, I hope you've enjoyed this, and I hope you've learned something. Thank you for joining me. Please like and subscribe, and bye-bye.